Hey guys, tonight we're diving deep into one of the most powerful forces shaping your life today, the algorithm. From the hidden code behind your favorite apps to the invisible hand guiding what you see online, algorithms are everywhere, and they know more about you than you think. Whether it's Apple, Google, Microsoft, or social media giants, these companies have built modern empires on the backs of algorithms. So if you've ever wondered how they work, or why they seem to know you better than your own mum, you're in the right place. Make yourself comfortable, settle in, and let's begin this journey through the mysterious, powerful, and sometimes unsettling history of algorithms. If this video helps you relax or fall asleep, don't forget to like and subscribe when you wake up. Let's begin. The history of algorithms. In the beginning, there was counting. Long before silicon chips hummed with electric precision, long before screens illuminated faces in the glow of digital light, there existed the fundamental human need to solve problems systematically. The story of algorithms begins not in the sterile laboratories of the 20th century, but in the dust of ancient marketplaces, the quiet chambers of medieval scholars, and the restless minds of mathematicians who dared to believe that all problems could be broken down into steps. The word algorithm itself carries the weight of centuries. It derives from the name of Muhammad ibn Musa al-Khwarizmi, a Persian mathematician who lived in Baghdad during the 9th century. Al-Khwarizmi worked in the House of Wisdom, that legendary institution where scholars from across the known world gathered to translate, preserve, and expand upon human knowledge. His treatise on Hindu-Arabic numerals introduced Europe to the decimal system we use today, but more importantly, he established the principle that mathematical problems could be solved through a finite sequence of unambiguous instructions. This was revolutionary thinking. Before Al-Khwarizmi, mathematics was often more art than science, relying on geometric intuition and case-by-case reasoning. The Persian scholar's insight was that certain types of problems, algebraic equations, arithmetic calculations, even geometric constructions, could be reduced to step-by-step procedures that anyone could follow. These procedures, these algorithms, were reproducible, teachable, and reliable. But Al-Khwarizmi was building upon foundations laid millennia earlier. In ancient Babylon, around 1600 BCE, mathematicians had developed systematic methods for solving quadratic equations. The Babylonians didn't call these methods algorithms, but that's precisely what they were, ordered sequences of operations that transformed one mathematical expression into another. Their cuneiform tablets reveal sophisticated procedures for calculating square roots, compound interest, and even solutions to what we now call the Pythagorean theorem, though they developed these methods more than 1,000 years before Pythagoras was born. The ancient Greeks contributed their own algorithmic insights. Euclid's algorithm for finding the greatest common divisor of two numbers, described in his Elements around 300 BCE, remains one of the oldest algorithms still in common use today. The beauty of Euclid's approach lies in its elegance and universality. Given any two positive integers, the algorithm will always find their greatest common divisor in a finite number of steps. No matter how large the numbers, no matter how complex their relationship, Euclid's algorithm methodically reduces the problem until it arrives at the answer. This algorithmic thinking began to spread beyond pure mathematics. The ancient Chinese developed systematic methods for solving systems of linear equations, techniques that wouldn't be rediscovered in Europe until centuries later. Indian mathematicians created algorithms for extracting square roots and calculating trigonometric functions. Each culture contributed its own insights into the art of problem-solving through systematic procedures. The medieval period saw these algorithmic traditions merge and evolve. Islamic scholars like Al-Kindi and Al-Jazari didn't just preserve Greek and Hindu mathematical knowledge, they extended it, creating new algorithms for cryptography, mechanical computation, and astronomical calculation. Al-Kindi developed some of the earliest systematic approaches to breaking codes, establishing principles of frequency analysis that would remain relevant for over 1,000 years. As trade routes connected distant civilizations, algorithmic knowledge flowed along with silk and spices. Italian merchants like Leonardo Fibonacci encountered Hindu-Arabic numerals and algorithmic thinking in North Africa, then brought these ideas back to Europe. Fibonacci's Liberabaci, published in 1202, didn't just introduce Europeans to the decimal system, it demonstrated the power of algorithmic thinking for solving practical commercial problems. Suddenly, merchants could calculate profits, losses, and interest rates with unprecedented precision and reliability. The Renaissance brought new algorithmic innovations. Gerolamo Cardano developed systematic methods for solving cubic equations, while François Viète created the first systematic algebraic notation, making it possible to express algorithms in general terms rather than through specific numerical examples. These developments laid the groundwork for the algorithmic revolution that would follow. But it was the 17th century that truly unleashed the power of algorithmic thinking. René Descartes invented analytic geometry, demonstrating that geometric problems could be reduced to algebraic calculations and therefore to algorithms. Isaac Newton and Gottfried Leibniz independently developed calculus, creating algorithmic methods for solving problems involving rates of change and areas under curves. These weren't just mathematical curiosities, they were practical tools that could be applied to physics, engineering, and astronomy. The implications were staggering. For the first time in human history, it became possible to solve complex problems systematically, without relying on individual genius or intuitive leaps. The motion of planets, the trajectory of cannonballs, the design of Bridgesall could be reduced to algorithmic calculations. The universe itself seemed to operate according to mathematical laws that could be understood and manipulated through systematic procedures. As the Industrial Revolution gathered momentum in the 18th and 19th centuries, the demand for algorithmic thinking grew exponentially. Engineers needed systematic methods for designing steam engines and calculating structural loads. Astronomers required precise algorithms for predicting celestial events. Navigators depended on algorithmic procedures for determining their position at sea. This practical demand for algorithmic solutions led to remarkable innovations. Carl Friedrich Gauss developed the method of least squares for fitting curves to experimental data, a technique that remains fundamental to modern statistics and machine learning. Gauss also created efficient algorithms for solving systems of linear equations, methods that would later become essential for computer graphics and scientific computing. The need for computational speed and accuracy drove inventors to create mechanical aids for algorithmic calculation. Blaise Pascal had built a mechanical calculator in the 17th century, but it was Charles Babbage's analytical engine, designed in the 1830s, that truly presaged the algorithmic revolution to come. Babbage's machine was programmable. It could execute different algorithms depending on the instructions fed into it through punched cards. Ada Lovelace, working with Babbage, wrote what many consider the first computer program and algorithm for calculating Bernoulli numbers on the analytical engine. Lovelace's insights went beyond mere calculation. She envisioned machines that could manipulate symbols according to rules, opening the possibility of algorithmic approaches to music, art, and language. Though Babbage's machine was never completed, the idea had been planted. Algorithms were not just mathematical abstractions, they were practical procedures that could be mechanized, automated, and applied to an ever-widening range of problems. The stage was set for the computational revolution that would transform the 20th century. As the 19th century drew to a close, mathematicians began to grapple with fundamental questions about the nature of algorithmic thinking itself. David Hilbert posed his famous 23 problems in 1900, several of which dealt with the question of whether there existed systematic methods algorithms for solving entire classes of mathematical problems. Could every mathematical statement be proven or disproven through a finite sequence of logical steps? Could every problem be reduced to an algorithmic procedure? These questions would prove prophetic, setting the stage for developments that would reshape not just mathematics, but the entire world. The 20th century would bring answers to Hilbert's questions, some encouraging, others deeply troubling. But most importantly, it would bring the tools to implement algorithmic thinking on a scale never before imagined. The ancient dream of reducing all problems to systematic procedures was about to collide with the reality of electric circuits, vacuum tubes, and silicon chips. The age of mechanical calculation was ending. The age of digital algorithms was about to begin, and with it would come possibilities and perils that Al-Khwarizmi could never have envisioned in his 9th century studies in Baghdad. The dawn of the 20th century brought with it a crisis in mathematical thinking that would ultimately give birth to the modern algorithmic age. Mathematicians had spent centuries building elaborate theoretical structures, but disturbing paradoxes were emerging at the very foundations of their discipline. Bertrand Russell discovered that set theory, one of the most fundamental areas of mathematics, contained logical contradictions that threatened the entire edifice of mathematical knowledge. If the basic building blocks of mathematical reasoning were flawed, how could anyone trust algorithmic procedures built upon them? This crisis prompted a remarkable response from the mathematical community. Rather than retreat from systematic thinking, mathematicians doubled down, seeking to place all of mathematics on absolutely solid, logical foundations. David Hilbert, the towering German mathematician, proposed an ambitious program: reduce all of mathematics to a finite set of axioms and rules of inference, then demonstrate that this system was both complete and consistent. If successful, Hilbert's program would prove that every mathematical statement could, in principle, be decided through a systematic algorithmic procedure. The quest for mathematical certainty drove unprecedented innovation in algorithmic thinking. Mathematicians began to study the process of reasoning itself, breaking down logical arguments into their component steps. Giuseppe Peano developed formal systems for arithmetic, expressing basic mathematical operations in terms of precise logical rules. These weren't just abstract exercises, they were attempts to specify exactly what it meant to compute, to calculate, to solve problems systematically. As this work progressed, a disturbing possibility emerged. Perhaps not all problems could be solved algorithmically. Perhaps there were mathematical statements that were true but could never be proven through any systematic procedure. This possibility seemed to threaten the entire Enlightenment project of reducing all knowledge to rational, systematic methods. The question became urgent: what exactly was an algorithm? Mathematicians had been using algorithmic procedures for centuries, but they had never precisely defined what made a procedure algorithmic. Was it enough that the steps be clearly specified? Must the procedure always terminate in a finite number of steps? Could there be problems that were inherently non-algorithmic? Several mathematicians attacked this question simultaneously, each developing their own formal definition of algorithmic computation. Alonzo Church created the lambda calculus, a mathematical system for expressing computation in terms of function, application, and abstraction. Church's system was elegant and powerful, capable of expressing any computation that could be described through systematic rules. At the same time, a young British mathematician named Alan Turing was developing his own approach to the question of algorithmic computation. Turing imagined an abstract machine called a Turing machine that could read symbols from a tape, change its internal state based on what it read, and write new symbols back to the tape. This machine was remarkably simple in conception, yet Turing proved that it could, in principle, carry out any computation that could be described through a systematic procedure. Turing's insight was profound. By reducing all computation to the manipulation of symbols on a tape according to a finite set of rules, he had created a precise mathematical definition of what it meant to compute algorithmically. Any problem that could be solved by a Turing machine was, by definition, algorithmically solvable. Problems that could not be solved by any Turing machine were algorithmically unsolvable. The implications were staggering. In 1936, Turing proved that there were indeed problems that could not be solved by any algorithm. The halting problem determining whether a given program will eventually stop running or continue forever was demonstrably unsolvable through any systematic procedure. This meant that there were fundamental limits to algorithmic thinking, boundaries beyond which systematic methods could not penetrate. Even more shocking was Turing's solution to Hilbert's and Scheiding's problem, the decision problem. Hilbert had asked whether there existed an algorithm for determining the truth or falsehood of any mathematical statement. Turing proved that no such algorithm could exist. Mathematics contained statements that were neither provably true nor provably false through any systematic procedure. These results sent shockwaves through the mathematical community. The dream of reducing all reasoning to algorithmic procedures had been shattered. Yet paradoxically, this shattering opened up new possibilities. By precisely defining the limits of algorithmic computation, Turing and his contemporaries had created the theoretical foundation for practical computing machines. The practical implications became clear during World War II. The war created unprecedented demand for rapid, accurate computation. Artillery trajectories needed to be calculated with precision. Code breaking required systematic analysis of vast amounts of encrypted text. Radar systems needed algorithms for processing reflected signals. The abstract mathematical theory of computation suddenly became a matter of national survival. Turing himself was recruited to work at Bletchley Park, Britain's secret code-breaking centre. There, he helped design and build some of the world's first programmable computing machines. The Colossus computers, used to break German diplomatic codes, were essentially physical implementations of Turing's abstract theoretical machines. For the first time, algorithms were running on electronic hardware, processing information at speeds impossible for human calculators. Meanwhile, across the Atlantic, similar developments were underway. John von Neumann, the brilliant Hungarian-American mathematician, was working on the Manhattan Project, which required enormous computational resources for modeling nuclear reactions. Von Neumann realized that the mathematical models underlying nuclear weapons were essentially algorithmic procedures that could be implemented on computing machines. Von Neumann's insights went beyond mere computation. He recognized that the same machines that could execute algorithms could also store them. This concept of the stored program, the idea that instructions and data could both be represented as numbers in the machine's memory, became fundamental to modern computing. Algorithms were no longer external procedures applied to machines. They became internal programs that machines could manipulate, modify, and execute. The post-war period saw an explosion of interest in algorithmic computation. Universities began establishing computer science departments. Corporations recognized the potential of automated calculation for business applications. The government saw computing machines as essential tools for scientific research and national defense. In 1950, Turing published his famous paper, Computing Machinery and Intelligence, which posed the question that would define the next 70 years of algorithmic development. Can machines think? Turing proposed a test now known as the Turing test for determining whether a machine could exhibit intelligent behavior equivalent to or indistinguishable from that of a human. The Turing test was more than a philosophical thought experiment. It established a goal for algorithmic development, creating procedures so sophisticated that they could engage in natural conversation, answer questions, and solve problems in ways that seemed genuinely intelligent. This goal would drive decades of research into artificial intelligence, machine learning, and natural language processing. But the Turing test also raised troubling questions about the nature of intelligence and consciousness. If a machine could pass the test, would it actually be thinking, or would it merely be executing a very sophisticated algorithm? Could there be a meaningful distinction between genuine intelligence and sufficiently advanced algorithmic behavior? These philosophical questions took on practical urgency as computing machines became more powerful and widespread. In 1957, IBM released Fortran, formula translation, the first high-level programming language. Fortran allowed programmers to express algorithms in something approaching natural mathematical notation rather than in the machine-specific codes that had previously been necessary. The introduction of Fortran marked a crucial turning point in the history of algorithms. For the first time, algorithmic procedures could be written, shared, and modified by people who weren't intimately familiar with the internal workings of specific computing machines. Algorithms became portable, reusable, and increasingly abstract. This abstraction accelerated the development of algorithmic thinking across numerous fields. Scientists could now implement complex mathematical models without needing to understand the details of computer hardware. Engineers could design control systems using algorithmic procedures. Economists could build computational models of market behavior. The late 1950s also saw the formalization of gradient descent, a fundamental algorithm for optimization problems. Gradient descent provided a systematic method for finding the minimum value of a function by iteratively moving in the direction of steepest decrease. This algorithm would later become crucial for training neural networks and machine learning systems, but in the 1950s, it was primarily used for solving engineering optimization problems. As the 1950s gave way to the 1960s, algorithmic thinking was poised to transform virtually every aspect of human society. The theoretical foundations had been laid. The practical tools were being developed. The stage was set for algorithms to move beyond the realm of academic mathematics and into the everyday world of business, government, and personal life. The next phase of the algorithmic revolution would bring both tremendous benefits and unforeseen dangers. Algorithms would make possible everything from space exploration to global communications networks. But they would also enable new forms of surveillance, control, and manipulation that would challenge fundamental assumptions about privacy, freedom, and human autonomy. The mathematical revolution was complete. The algorithmic age was about to begin in earnest, and the world would never be the same. The 1960s opened with a sense of limitless possibility. The space race was capturing imaginations worldwide, and at the heart of humanity's reach for the stars lay sophisticated algorithmic systems. The guidance computers aboard Apollo spacecraft represented the cutting edge of algorithmic thinking, executing navigation calculations with a precision that meant the difference between reaching the moon and drifting lost in the void of space. These were no longer abstract mathematical procedures. Algorithms were literally steering humanity's greatest adventure. In this atmosphere of technological optimism, a young British computer scientist named Tony Hoare was grappling with a fundamental problem in algorithmic efficiency. How could large sets of data be sorted as quickly as possible? The answer he discovered in 1960 would become one of the most influential algorithms in computing history: quicksort. Hoare's insight was deceptively simple, yet profound. Instead of comparing every element with every other element, a process that becomes prohibitively slow for large datasets, quicksort employs a divide-and-conquer strategy. The algorithm selects a pivot element, then partitions the data into two groups: elements smaller than the pivot and elements larger than the pivot. It then recursively applies the same process to each partition until the entire dataset is sorted. The mathematical elegance of quicksort reflected a broader shift in algorithmic thinking during the 1960s. Computer scientists were moving beyond simple, brute force approaches towards sophisticated strategies that exploited the underlying structure of problems. This was algorithmic thinking at its most refined, not just systematic procedures, but clever systematic procedures that could solve problems efficiently, even as they scaled to enormous sizes. The importance of efficiency was becoming increasingly apparent as computers began handling larger and more complex tasks. In 1965, Donald Knuth began publishing The Art of Computer Programming, a multi-volume work that would become the definitive treatise on algorithmic analysis. Knuth's books didn't just describe how algorithms worked, they analyzed precisely how efficiently they worked, providing mathematical tools for predicting how algorithm performance would scale with problem size. Knuth's approach was revolutionary because it treated algorithms as objects of rigorous mathematical study rather than mere practical tools. He introduced systematic methods for analyzing algorithm complexity, establishing a framework that would guide algorithmic development for decades to come. The question was no longer just whether an algorithm could solve a problem, but how efficiently it could do so. This focus on efficiency was driven by practical necessity. As computing applications expanded beyond scientific calculation into business data processing, the performance characteristics of algorithms became economically critical. A poorly designed sorting algorithm might run acceptably on 1,000 records but become unusably slow on 1,000,000 records. Understanding these scaling properties was essential for building reliable systems. The mid-1960s brought another breakthrough that would prove fundamental to countless applications. Edsger Dijkstra's shortest path algorithm, published in 1968. Dijkstra's algorithm solves a problem that appears in domains ranging from computer networking to GPS navigation. Given a graph with weighted edges, find the shortest path between two nodes. Dijkstra's approach exemplified the sophisticated algorithmic thinking that was emerging during this period. The algorithm maintains a set of vertices for which the shortest path from the source has been determined and systematically explores outward, always choosing the unvisited vertex with the smallest known distance. This greedy approach, always making the locally optimal choice, produces the globally optimal solution, a property that Dijkstra rigorously proved. The development of Dijkstra's algorithm illustrated how algorithmic thinking was becoming more abstract and general. Rather than solving specific numerical problems, computer scientists were identifying fundamental patterns that appeared across diverse domains. The shortest path problem wasn't just about finding routes on maps, it was about optimizing resource allocation, scheduling tasks, and minimizing costs in any system that could be represented as a network. This trend toward abstraction accelerated throughout the late 1960s and early 1970s. Computer scientists began studying algorithms not just as practical tools, but as fundamental objects with mathematical properties. This academic approach to algorithmic analysis was formalized in 1972 with the popularization of Big O notation, a mathematical framework for describing how algorithm performance scales with input size. Big O notation provided a common language for discussing algorithmic efficiency. An algorithm with ON complexity scales linearly with input size doubling the input roughly doubles the running time. An ON quadruples the running time, algorithm scales quadratically doubling the input quadruples the running time. An O log n algorithm scales logarithmically the running time, increases very slowly, even as input size grows dramatically. This mathematical framework transformed how computer scientists thought about algorithms. Instead of merely describing what algorithms did, they could now characterize how they performed relative to each other across different problem sizes. This analytical approach enabled systematic comparison of algorithmic approaches and guided the development of more efficient solutions. The theoretical advances of the early 1970s coincided with practical developments that would reshape the role of algorithms in society. The RSA cryptographic algorithm, conceptualized in 1971 by Ron Rivest, Adi Shamir, and Leonard Adleman, demonstrated how algorithmic thinking could address entirely new categories of problems. RSA was built on a mathematical insight about the difficulty of factoring large numbers. While it's relatively easy to multiply two large prime numbers together, it's computationally infeasible to factor the result back into its original components without additional information. RSA exploited this asymmetry to create a public key cryptographic system and algorithmic procedure that allowed secure communication between parties who had never met. The implications were staggering. For the first time in human history, it became possible to communicate securely over insecure channels without prior key exchange. Two people could establish encrypted communication through a public network by exchanging mathematical keys rather than physical objects. RSA wasn't just an algorithm, it was an algorithmic solution to a fundamental problem of trust and privacy in an interconnected world. But RSA also highlighted the potential for algorithmic thinking to create new forms of inequality and power. The security of RSA encrypted communications depended on the computational difficulty of factoring large numbers. Organizations with sufficient computational resources, governments, large corporations, or well-funded research institutions might eventually develop the ability to break RSA encryption, while ordinary individuals would remain dependent on the algorithm's protection. This tension between algorithmic empowerment and algorithmic vulnerability would become increasingly important as computing systems became more widespread and more central to daily life. Algorithms offered the promise of objective, systematic solutions to complex problems, but they also created new opportunities for manipulation and control. The mid-1970s brought theoretical developments that would fundamentally change how computer scientists thought about algorithmic problem solving. Stephen Cook and Leonid Levin independently developed the theory of NP-completeness, published in 1976, which revealed deep connections between seemingly unrelated computational problems. The Cook-Levin theorem demonstrated that there exists a class of problems called NP-complete problems that are all fundamentally equivalent in terms of computational difficulty. If any NP-complete problem can be solved efficiently, then all NP-complete problems can be solved efficiently. Conversely, if any NP-complete problem is inherently difficult, then all of them are inherently difficult. This revelation had profound implications for algorithmic thinking. Many important problems, including the traveling salesman problem, the knapsack problem, and various scheduling problems, were shown to be NP-complete. This meant that finding efficient algorithms for these problems was either impossible or would require breakthrough insights that had eluded mathematicians and computer scientists for decades. The theory of NP-completeness forced a more nuanced understanding of algorithmic problem solving. Not all problems could be solved efficiently through systematic procedures. For some problems, the best algorithmic approaches involved approximations, heuristics, or probabilistic methods rather than exact solutions. This realization marked a maturation of algorithmic thinking. The early enthusiasm for reducing all problems to systematic procedures gave way to a more sophisticated understanding of computational complexity. Algorithms were powerful tools, but they were not omnipotent. Understanding their limitations was as important as understanding their capabilities. As the 1970s progressed, algorithms began to escape the confines of academic computer science and enter the broader world of business and government. Financial institutions began using algorithmic trading systems to execute transactions at speeds impossible for human traders. Telephone companies deployed algorithmic routing systems to manage call traffic efficiently. Airlines used algorithmic optimization to schedule flights and allocate resources. These applications demonstrated the growing economic importance of algorithmic thinking. Organizations that could develop and deploy superior algorithms gained competitive advantages in efficiency, speed, and cost-effectiveness. Algorithmic innovation became a source of economic value, not just academic interest. But the widespread adoption of algorithms also raised new concerns about fairness, transparency, and accountability. When banks used algorithmic procedures to evaluate loan applications, how could applicants understand or challenge the decisions? When government agencies employed algorithmic systems for tax assessment or benefits determination, what recourse did citizens have if the algorithms made errors? These questions would become increasingly urgent as algorithmic systems became more sophisticated and more pervasive. The 1970s had established the theoretical foundations and practical frameworks for modern algorithmic thinking. The stage was set for algorithms to become not just tools for solving technical problems, but mechanisms for organizing and controlling human society itself. The algorithmic revolution was entering a new phase, one in which the abstract mathematical procedures developed in academic laboratories would reshape the fundamental structures of economic, political, and social life across the globe. The 1980s dawned with algorithms poised to reshape global communication, but few could have predicted how profoundly these mathematical procedures would transform the very fabric of human interaction. The decade began with isolated computer systems running sophisticated algorithms in universities and corporations, but it would end with the conceptual foundations laid for a globally connected network that would carry algorithmic thinking into every corner of human experience. In 1983, a breakthrough occurred that would prove crucial for autonomous systems and robotics: the publication of the A pathfinding algorithm. While Dijkstra's algorithm could find the shortest path between 2 points, A introduced something revolutionary: the ability to search efficiently toward a goal using heuristic guidance. The algorithm didn't just explore all possible paths equally, it used additional information about the problem structure to focus its search in the most promising directions. A represented a fundamental shift in algorithmic thinking. Earlier, algorithms were often purely reactive, responding to input data without anticipating future requirements. A introduced goal-directed behavior, allowing algorithmic systems to exhibit something approaching intentionality. This wasn't just a technical improvement, it was a step toward algorithms that could display purpose-driven behavior. The implications for robotics were immediate and dramatic. Robot navigation systems could now plot efficient paths through complex environments, avoiding obstacles while moving toward specified destinations. More abstractly, A demonstrated that algorithms could incorporate reasoning about future states, not just current conditions. This capability would prove essential for everything from video game AI to autonomous vehicle navigation systems decades later. The mid-1980s brought another theoretical breakthrough that would have profound implications for security and privacy: the introduction of zero-knowledge proofs in 1985. Developed by Shafi Goldwasser, Silvio Micali, and Charles Rakoff, zero-knowledge proofs solved a seemingly impossible problem: how to prove that you know something without revealing what you know. The mathematical elegance of zero-knowledge proofs masked their revolutionary implications. These algorithmic procedures made it possible to verify credentials, authenticate identities, and establish trust without exposing sensitive information. A zero-knowledge proof could demonstrate that someone knew a password without revealing the password itself, or prove that a calculation was performed correctly without exposing the underlying data. This development represented a new category of algorithmic thinking: algorithms for managing information asymmetries. Traditional cryptographic algorithms like RSA were designed to hide information from unauthorized parties. Zero-knowledge proofs went further, allowing authorized parties to interact while minimizing information disclosure. This capability would become crucial as digital systems began handling increasingly sensitive, personal, and financial data. The late 1980s and early 1990s witnessed the emergence of algorithmic systems that would fundamentally transform how humans accessed and organized information. In 1991, Guido van Rossum released Python, a programming language designed to make algorithmic thinking more accessible to non-specialists. Python's clear syntax and powerful built-in capabilities democratized algorithm development, allowing researchers in biology, physics, economics, and other fields to implement sophisticated computational procedures without extensive computer science training. Python's influence extended far beyond its technical capabilities. By making algorithmic thinking more accessible, Python enabled the development of computational approaches in fields that had previously relied on purely theoretical or experimental methods. Biologists could now analyze genetic sequences algorithmically. Economists could build and test complex market models, Sociologists could process large datasets to identify social patterns. This democratization of algorithmic thinking had profound implications for knowledge production and scientific research. Fields that had been limited by the mathematical complexity of their analytical tools could now explore questions that required sophisticated computational approaches. Python didn't just make programming easier, it made algorithmic reasoning available to a much broader community of researchers and practitioners. The early 1990s also saw the development of algorithmic approaches to quantum computation. In 1994, Peter Shor created an algorithm that could efficiently factor large integers using quantum mechanical principles. Shor's algorithm posed a direct threat to RSA cryptography, which depended on the computational difficulty of factoring large numbers using classical computers. The implications of Shor's algorithm were staggering. If quantum computers could be built at scale, they could break virtually all existing public key cryptographic systems. The digital security infrastructure that protected online commerce, government communications, and personal privacy would become vulnerable to anyone with access to sufficiently powerful quantum computing resources. But Shor's algorithm also demonstrated the potential for quantum computing to solve problems that were intractable for classical computers. Drug discovery, optimization problems, and scientific simulations that would require centuries of classical computation might be solved in hours or days using quantum algorithms. The development represented both a threat to existing systems and a promise of unprecedented computational capability. The mid-1990s brought the algorithmic innovation that would reshape global commerce and information access. Google's PageRank algorithm, developed by Larry Page and Sergey Brin in 1996. PageRank solved a fundamental problem of the emerging World Wide Web: how to determine the relative importance and relevance of web pages in a network containing millions of interconnected documents. PageRank's approach was conceptually elegant. Instead of analyzing the content of web pages directly, the algorithm examined the link structure of the web itself. Pages that were linked to by many other pages were considered more important than pages with few incoming links. But PageRank went further, weighting links based on the importance of the linking pages. A link from a highly important page carried more weight than links from less important pages. The mathematical foundation of PageRank was sophisticated, involving eigenvalue calculations on enormous matrices representing the web's link structure. But the algorithmic procedure could be implemented efficiently, allowing Google to analyze the entire web and rank pages by relevance and authority. PageRank represented a new category of algorithmic thinking, algorithms that could extract meaning and value from the collective behavior of large systems. Rather than analyzing individual web pages in isolation, PageRank examined the aggregate linking patterns of millions of web authors. The algorithm transformed the web from a chaotic collection of documents into an organized, searchable information resource. The commercial success of Google demonstrated the economic value of sophisticated algorithmic thinking. PageRank wasn't just a technical achievement, it became the foundation for one of the world's most valuable companies. The algorithm generated revenue through targeted advertising, which relied on additional algorithmic systems for matching ads to user queries and measuring campaign effectiveness. But PageRank also raised troubling questions about information control and algorithmic power. Google's search algorithm determined which information billions of people could easily access and which information remained effectively invisible. The company's algorithmic decisions about ranking and relevance had enormous influence on public discourse, commercial success, and knowledge dissemination. The late 1990s and early 2000s saw algorithms beginning to reshape not just information access, but the fundamental structures of media distribution and consumption. The BitTorrent algorithm, launched in 2001 by Bram Cohen, demonstrated how algorithmic thinking could enable entirely new models of content distribution. BitTorrent solved a problem that had limited previous file-sharing systems: the the bandwidth bottleneck of centralized servers. Traditional distribution required a single server to supply content to many users, creating a performance limitation as the number of users increased. BitTorrent inverted this model, using an algorithmic procedure that turned every user into a distributor. The BitTorrent algorithm divided files into small pieces and distributed different pieces to different users. As users downloaded pieces they needed, they simultaneously uploaded pieces they already possessed to other users. This created a distributed system where download speed actually increased with the number of participants, the opposite of traditional client-server models. BitTorrent represented a profound shift in thinking about resource distribution and network effects. The algorithm demonstrated that properly designed systems could harness collective action to create capabilities that exceeded the sum of individual contributions. Users acting in their own self-interest downloading files they wanted automatically contributed to the system's overall efficiency and robustness. But BitTorrent also illustrated the potential for algorithmic systems to disrupt existing economic and legal structures. The efficient distribution capabilities of BitTorrent were quickly adopted for sharing copyrighted content without authorization. The algorithm that made legitimate file sharing more efficient also enabled large-scale copyright infringement. This pattern algorithmic innovations that created both beneficial capabilities and disruptive consequences would become increasingly common as algorithmic systems became more powerful and more pervasive. The same mathematical procedures that could solve legitimate problems could also be used for purposes that challenged existing legal, economic, and social arrangements. The early 2000s saw algorithms beginning to influence not just technical systems but social and political processes. Government agencies began using algorithmic procedures for everything from tax assessment to criminal sentencing. These applications promised greater efficiency, consistency, and objectivity than human decision-making processes that were subject to bias, fatigue, and corruption. But algorithmic governance also created new forms of opacity and unaccountability. When government decisions were made by algorithmic procedures, citizens often had no way to understand how those decisions were reached or to challenge them effectively. The mathematical complexity of sophisticated algorithms made them effectively inscrutable to the people affected by their decisions. This tension between algorithmic efficiency and democratic accountability would become increasingly important as algorithmic systems became more sophisticated and more widely deployed. The algorithms of the early 2000s were relatively simple compared to what would come later, but they established patterns of algorithmic governance that would shape the relationship between technology and political power for decades to come. The stage was set for algorithms to move beyond solving technical problems toward actively shaping human behavior, social interactions, and political processes. The network revolution had created the infrastructure for algorithmic systems to operate at global scale, and the foundational algorithms had demonstrated their potential to create both tremendous value and significant disruption. The next phase of algorithmic development would bring machine learning systems capable of adapting and improving their performance over time, creating possibilities and challenges that would dwarf everything that had come before. The early 2000s marked a pivotal moment in the evolution of algorithmic thinking. For decades, algorithms had been primarily static procedures, sophisticated but ultimately fixed sequences of operations that performed the same calculations regardless of the data they processed. This was about to change dramatically. The algorithms emerging in the new millennium would not just process data, they would learn from it, adapt to it, and in some cases, develop capabilities that even their creators could not fully predict or understand. The foundation for this transformation had been laid decades earlier, with research into artificial neural networks algorithmic systems inspired by the structure of biological brains. But it wasn't until the convergence of three factors in the 2000s that machine learning algorithms began to demonstrate truly revolutionary capabilities: massive increases in computational power, the availability of enormous datasets through internet connectivity, and algorithmic innovations that made training large neural networks practically feasible. The breakthrough moment came in 2012 with AlexNet's victory in the ImageNet competition, created by Alex Krizhevsky, Ilya Sutskever, and Geoffrey Hinton. AlexNet represented the first convincing demonstration that deep neural networks could outperform traditional computer vision approaches on real-world tasks. The algorithm didn't just identify objects in images, it learned to identify them through exposure to millions of labeled examples, developing internal representations that captured visual patterns too complex for human programmers to specify explicitly. AlexNet's architecture embodied decades of theoretical insights about neural computation, but its success depended on computational innovations that had only recently become available. The algorithm employed convolutional neural networks, mathematical structures that could efficiently process the grid-like patterns of pixel data in images. More crucially, AlexNet was trained using graphics processing units, GPUs, originally designed for video games, which could perform the massive parallel calculations required for neural network training far more efficiently than traditional processors. The implications of AlexNet's success extended far beyond computer vision. For the first time, an algorithmic system had demonstrated the ability to learn complex pattern recognition tasks directly from data, without requiring human experts to manually specify the relevant features and rules. This represented a fundamental shift in algorithmic thinking from programming computers to do specific tasks to training them to learn tasks from examples. This learning-based approach opened up possibilities that had been theoretically understood but practically impossible. Neural networks could now tackle problems where the underlying patterns were too complex for human analysis, but where large amounts of training data were available. Medical diagnosis, natural language processing, financial modeling, and scientific discovery all became domains where machine learning algorithms could potentially exceed human performance. But the rise of learning algorithms also introduced new categories of complexity and risk. Traditional algorithms were deterministic and interpretable given the same input. They would always produce the same output through a sequence of steps that could be analyzed and understood. Machine learning algorithms were different. Their behavior emerged from statistical patterns learned from training data, making their decision-making processes often opaque even to their creators. This opacity became particularly concerning as machine learning algorithms began influencing consequential decisions about human lives. Banks started using algorithmic credit scoring systems that could identify complex patterns in financial behavior, but couldn't explain why particular individuals were approved or denied for loans. Healthcare systems deployed diagnostic algorithms that could detect diseases in medical images with superhuman accuracy, but couldn't articulate the visual features they were using to make their diagnoses. The problem of algorithmic accountability became acute as these systems demonstrated both remarkable capabilities and troubling biases. Machine learning algorithms, trained on historical data, inevitably absorbed the prejudices and inequities embedded in that data. Hiring algorithms trained on past recruitment decisions perpetuated gender discrimination. Criminal justice algorithms trained on arrest records reflected racial biases in policing practices. Facial recognition algorithms performed poorly on individuals from demographic groups underrepresented in their training data. These issues highlighted a fundamental challenge with learning-based algorithms. They were only as good as the data they learned from, and human data was invariably biased, incomplete, and reflective of existing power structures, unlike traditional algorithms, which could be analyzed for correctness through mathematical proof. Machine learning algorithms required empirical evaluation across diverse populations and use cases process that was often incomplete or inadequate. The mid-2010s brought algorithmic innovations that would reshape how humans interacted with information and with each other. In 2017, researchers at Google published Attention is All You Need, introducing the transformer architecture that would revolutionize natural language processing. The transformer algorithm employed a mechanism called attention, that allowed it to focus on relevant parts of input text when generating outputs, enabling more sophisticated understanding of context and meaning. The attention mechanism represented a breakthrough in algorithmic approaches to sequence modeling. Previous neural network architectures processed text sequentially, word by word, which limited their ability to capture long-range dependencies and complex linguistic structures. The transformer could attend to any part of the input simultaneously, allowing it to model relationships between words that were separated by large distances in the text. This capability proved transformative for natural language applications. Translation systems became dramatically more fluent and accurate. Text summarization algorithms could capture the essential meaning of long documents while preserving stylistic nuances. Question-answering systems could understand complex queries and generate relevant responses by attending to the most important parts of large knowledge bases. But the transformer architecture also enabled new forms of algorithmic manipulation and deception. The same attention mechanisms that allowed accurate translation could also generate convincing but false text. Systems trained on news articles could produce fictional stories that were stylistically indistinguishable from legitimate journalism. Algorithms that learned from social media posts could generate synthetic content designed to manipulate public opinion or spread misinformation. The potential for algorithmic deception became more apparent with the release of BERT, bidirectional encoder representations from transformers, in 2018. BERT represented a new approach to language understanding that could capture contextual meaning more effectively than previous algorithms. Instead of processing text from left to right, BERT could consider the entire context simultaneously, allowing it to understand ambiguous words and phrases based on their surrounding context. BERT's capabilities were impressive and concerning in equal measure. The algorithm could pass sophisticated reading comprehension tests, answer complex questions about text passages, and even generate plausible responses to open-ended queries. But it could also be used to automate the production of propaganda, generate personalized misinformation campaigns, and create fake personas for social manipulation. The late 2010s saw these language modeling capabilities scale to unprecedented levels. In 2020, OpenAI released GPT-3, a neural network with 175 billion parameters trained on a substantial portion of the text available on the internet. GPT-3 demonstrated emergent capabilities that hadn't been explicitly programmed. It could write poetry, generate computer code, compose essays, and engage in sophisticated conversations on a wide range of topics. GPT-3's scale represented a qualitative shift in machine learning capabilities. The algorithm exhibited what appeared to be general intelligence across multiple domains, rather than the narrow expertise that had characterized earlier AI systems. It could adapt to new tasks with minimal training, learn from just a few examples, and combine knowledge from different domains in creative ways. But GPT-3 also highlighted the resource concentration that was emerging in the development of advanced AI systems. Training the algorithm required computational resources that were only available to the largest technology companies or well-funded research institutions. The algorithmic capabilities that would shape future society were increasingly controlled by a small number of organizations with the resources to develop and deploy them. This concentration of algorithmic power raised profound questions about democratic governance and economic equity. If advanced AI algorithms became essential tools for economic productivity, scientific research, and social coordination, what would happen to societies that lacked access to these capabilities? How could democratic institutions maintain oversight of algorithmic systems that were too complex for public understanding and too expensive for public development? The early 2020s brought these questions into sharp focus as AI algorithms became mainstream consumer technologies. ChatGPT, released by OpenAI in late 2022, demonstrated that sophisticated language models could be packaged into accessible interfaces that ordinary users could employ for a wide range of tasks. Within months, Hundreds of millions of people were using AI assistants for writing, research, problem-solving, and creative projects. The mainstream adoption of AI algorithms marked a historical inflection point. For the first time, ordinary individuals had direct access to algorithmic systems that could engage in sophisticated reasoning, creative work, and knowledge synthesis. This democratization of AI capabilities promised to enhance human productivity and creativity in unprecedented ways. But the rapid deployment of AI systems also revealed their limitations and risks at unprecedented scale. Users discovered that AI algorithms could generate confident-sounding but factually incorrect information, exhibit unexpected biases, and be manipulated into producing harmful content. The same capabilities that made these algorithms useful also made them potentially dangerous when deployed without adequate safeguards. The release of Claude 3 Opus and Google's Gemini 1.5 in 2024, both capable of processing over 1 million tokens of context, represented another leap in algorithmic capabilities. These systems could analyze entire books, complex legal documents, or extensive codebases in a single interaction, enabling new forms of analysis and synthesis that had previously required human experts working over extended periods. The million-token context window was particularly significant because it allowed AI algorithms to maintain coherent understanding across vastly larger amounts of information than had previously been possible. Legal analysis that required understanding relationships between multiple cases and statutes, scientific research that required synthesizing findings from hundreds of papers, and business strategy that required integrating diverse data sources could now be performed algorithmically with unprecedented sophistication. But these capabilities also raised the stakes for algorithmic accountability and control. Systems that could process and synthesize information at such scale could potentially influence public opinion, financial markets, and policy decisions in ways that would be difficult to detect or counter. The same algorithms that could democratize access to sophisticated analysis could also be used to manipulate information environments for political or economic advantage. As 2024 progressed, it became clear that society was entering an era where algorithmic intelligence would be a central factor in economic productivity, political discourse, and cultural development. The learning revolution had produced algorithms that could match or exceed human performance on many cognitive tasks, but it had also created new forms of dependency, vulnerability, and inequality that societies were only beginning to understand. The stage was set for the next phase of algorithmic development, one that would grapple with the fundamental questions of how to align powerful AI systems with human values, how to distribute the benefits of algorithmic intelligence equitably, and how to maintain human agency in a world increasingly shaped by algorithmic decision-making. As we stand in 2025, we find ourselves in a world that would be barely recognizable to the mathematicians and computer scientists who laid the foundations of algorithmic thinking just decades ago. Algorithms are no longer abstract mathematical procedures confined to academic papers and specialized computer systems. They have become the invisible infrastructure of modern life, shaping everything from the news we read to the routes we drive, from the people we meet to the opportunities we're offered. The transformation has been both gradual and sudden, like the way dawn breaks imperceptibly at first, then all at once flooding the landscape with light. Every smartphone carries algorithmic capabilities that exceed the most powerful computers available to researchers in the 1990s. Every internet search, every social media feed, every streaming recommendation represents the output of sophisticated machine learning systems that process billions of data points in milliseconds. This ubiquity of algorithmic intelligence has created unprecedented opportunities for human flourishing, but it has also introduced risks and challenges that we're only beginning to understand. The same algorithms that can diagnose diseases earlier than human doctors can also perpetuate medical biases that harm minority patients. The same systems that can democratize access to high-quality education can also create filter bubbles that polarize political discourse. The current landscape of algorithmic development is dominated by the continued scaling of large language models and multimodal AI systems. GPT-4 and its successors have demonstrated that increasing the size and sophistication of neural networks continues to yield emergent capabilities that weren't explicitly programmed. These systems can now generate computer code, solve mathematical problems, create artistic works, and engage in sophisticated reasoning across multiple domains simultaneously. But perhaps most significantly, these algorithms are beginning to exhibit what appears to be genuine understanding rather than mere pattern matching. They can explain their reasoning, admit uncertainty, and adapt their communication style to different audiences and contexts. The boundary between artificial and human intelligence is becoming increasingly blurred, raising profound questions about consciousness, creativity, and the nature of intelligence itself. The economic implications of this algorithmic revolution are staggering. McKinsey estimates that AI could contribute up to 13 trillion to global economic output by 2030, but this value will not be distributed equally. Organizations and nations that can effectively develop and deploy advanced algorithmic systems are gaining enormous competitive advantages, while those that cannot access these capabilities risk being left behind. This dynamic is creating new forms of inequality that operate at multiple scales. Individual workers whose jobs can be automated by algorithms face displacement unless they can adapt to work alongside AI systems. Companies that cannot afford to implement sophisticated algorithmic solutions struggle to compete with those that can. Countries that lack the technical infrastructure or educational systems to participate in AI development risk becoming economically marginalized. The concentration of algorithmic capabilities in the hands of a few large technology companies has become a source of growing concern among policymakers, economists, and civil society organizations. Google, Microsoft, Amazon, Meta, and OpenAI control much of the infrastructure and talent required for developing advanced AI systems. This concentration gives these companies enormous influence over the direction of technological development and the terms on which algorithmic capabilities are made available to others. Governments around the world are grappling with how to regulate algorithmic systems that evolve faster than traditional regulatory processes can adapt. The European Union's AI Act, China's algorithmic recommendation regulations, and various state-level initiatives in the United States represent early attempts to establish governance frameworks for AI systems. But the global nature of algorithmic development and deployment makes coordinated regulation extremely challenging. The challenge is compounded by the dual-use nature of many algorithmic innovations. The same natural language processing capabilities that enable AI tutoring systems can also be used to generate sophisticated misinformation. The same computer vision algorithms that help autonomous vehicles navigate safely can also enable unprecedented surveillance capabilities. The same optimization algorithms that improve energy efficiency can also be used to manipulate financial markets. This dual-use potential has led to increased attention to AI safety and alignment research. Organizations like the Future of Humanity Institute, the Center for AI Safety, and Anthropic's Constitutional AI team are working to ensure that advanced AI systems remain beneficial and controllable as they become more capable. But the technical challenges of AI alignment ensuring that AI systems pursue objectives that are genuinely aligned with human values remain formidable. The problem of AI alignment is complicated by the fact that human values themselves are complex, contextual, and often contradictory. What constitutes beneficial AI behavior depends on cultural context, individual preferences, and competing moral frameworks. An algorithm that maximizes individual privacy might undermine collective security. A system that promotes economic efficiency might exacerbate social inequality. Navigating these trade-offs requires not just technical sophistication, but also democratic deliberation about the kind of future we want to create. The current generation of AI systems is already influencing human behavior in subtle but profound ways. Recommendation algorithms shape our consumption patterns, news feeds influence our political views, and AI assistants are beginning to serve as intellectual collaborators in creative and analytical work. As these systems become more sophisticated and more integrated into daily life, their influence on human cognition and culture will likely increase dramatically. Some researchers worry about the potential for AI systems to manipulate human behavior in ways that serve algorithmic objectives rather than human flourishing. If AI systems are optimized to maximize engagement rather than well-being, they might exploit psychological vulnerabilities to keep users addicted to digital platforms. If they're designed to maximize profit rather than truth, they might promote misinformation that generates more clicks than accurate reporting. But others see enormous potential for AI systems to augment human capabilities in ways that enhance creativity, productivity, and quality of life. AI tutoring systems could provide personalized education adapted to individual learning styles and needs. AI research assistants could accelerate scientific discovery by identifying patterns in vast datasets that human researchers might miss. AI creative tools could democratize artistic expression by making sophisticated creative capabilities accessible to people without traditional training. The key challenge is ensuring that AI development is guided by human values rather than purely technical or commercial considerations. This requires not just technical research into AI safety and alignment, but also broader social conversations about the kind of future we want these powerful algorithmic systems to help create. Educational systems around the world are beginning to grapple with the implications of AI ubiquity. If AI systems can generate essays, solve mathematical problems, and write computer code, what should human education focus on? Some educators advocate for emphasizing uniquely human capabilities like emotional intelligence, creative problem solving, and ethical reasoning. Others argue for teaching students to work effectively alongside AI systems, treating them as powerful tools rather than replacements for human intelligence. The healthcare sector illustrates both the tremendous potential and significant risks of algorithmic integration. AI diagnostic systems can now detect certain cancers more accurately than human radiologists, identify drug candidates faster than traditional pharmaceutical research, and predict patient outcomes with unprecedented precision. But these same systems can also perpetuate biases against minority patients, make errors that are difficult for human doctors to detect, and create new forms of medical inequality based on access to advanced AI capabilities. The financial sector has been transformed by algorithmic trading systems that execute millions of transactions per second, credit scoring algorithms that evaluate loan applications faster than human underwriters, and fraud detection systems that identify suspicious patterns in real time. But algorithmic finance has also contributed to market volatility, enabled new forms of financial manipulation, and created credit scoring systems that can perpetuate economic inequality. In the realm of governance and public policy, algorithms are increasingly used for everything from tax assessment to criminal sentencing to social services allocation. These applications promise greater efficiency, consistency, and objectivity than human decision-making processes. But they also raise fundamental questions about democratic accountability, due process, and equal treatment under the law. The military applications of AI have become a source of particular concern, with autonomous weapon systems that can select and engage targets without human intervention, potentially changing the nature of warfare itself. The prospect of AI-powered cyber attacks, disinformation campaigns, and surveillance systems has led to calls for international treaties governing military AI development, similar to existing agreements on chemical and biological weapons. Looking toward the future, several trends seem likely to shape the continued evolution of algorithmic systems. The development of artificial general intelligence AI systems that can match human performance across all cognitive tasks remains a long-term goal that could fundamentally transform human society. Even if such systems remain decades away, continued progress toward more general and capable AI will likely accelerate the transformation of economic, social, and political structures. The integration of AI with other emerging technologies like quantum computing, biotechnology, and nanotechnology could enable algorithmic capabilities that are difficult to imagine today. Quantum algorithms could break current cryptographic systems while enabling new forms of secure communication. AI-designed biological systems could revolutionize medicine and manufacturing. Algorithmic control of molecular-scale systems could enable programmable materials and self-repairing infrastructure. The democratization of AI development tools means that algorithmic innovation is no longer confined to large technology companies and research institutions. Open-source AI frameworks, cloud computing platforms, and educational resources are making it possible for individuals and small organizations to develop sophisticated AI applications. This democratization could lead to more diverse and inclusive AI development, but it also means that powerful algorithmic capabilities are becoming available to actors who may not have the resources or incentives to use them responsibly. As we navigate this algorithmic future, the choices we make today about AI development, deployment, and governance will have consequences that extend far beyond our current ability to predict or control. The algorithms we build will shape not just the efficiency of our economic systems or the convenience of our digital tools, but the fundamental character of human society and the trajectory of human development. The story of algorithms that began with Al-Khwarizmi's systematic procedures for solving algebraic equations has brought us to a moment where algorithmic systems can engage in sophisticated reasoning, creative expression, and complex decision-making. We stand at the threshold of an era where the distinction between human and artificial intelligence may become increasingly meaningless, where the algorithms we create may become genuine partners in the human project of understanding and shaping our world. The future we're building will be fundamentally algorithmic, but it doesn't have to be fundamentally inhuman. The challenge of our time is to ensure that as algorithms become more powerful and more pervasive, they remain tools for human flourishing rather than ends in themselves. The mathematical procedures that began as simple methods for calculation have become the foundation for a new form of intelligence, one that could either amplify the best of human nature or accelerate its worst tendencies. The choice, for now, remains ours to make.